All right, this video will continue our discussion of energy, talking about conservation of energy and then how to incorporate friction involved. So by the end of the video, we should be able to analyze a problem like this, which has, and this is pretty representative of a lot of energy problems. There's some initial situation, so you have a compressed spring up on a ramp, and then the final configuration, so it slides down the hill, it goes along some friction area, and you're supposed to find how far it slid across the friction surface. So frictionless up until right here, and then friction surface, you're supposed to solve for the coefficient of friction. So there's some initial moment and there's some final moment. And we'll use the fact that energy is conserved to solve for the requested variable. Okay, so to continue the discussion from last time and to tie this in with the book here, so we can write work done by a force is the integral of F, the force as a function of x over x from some initial to some final x value. And so we're going to have a lot more to say about this next chapter. So if the force is conservative, if F is conservative, and we're going to have more to say about this when we talk about forces in multiple dimensions. If the force is conservative, then you can write this integral, you can just evaluate this integral at the two endpoints. So there's some antiderivative function for F, and your book calls that G. So we'll call it G just for a few lines, and then we're going to have another variable that means a little bit more. So see how your book changes to U pretty quickly, and then there's no more mention of G ever again. So we'll do the same thing. So G is just the antiderivative. So the integral here is G evaluated at xf, and then minus is G evaluated at x initial. So there's a lot to say. So if F is conservative, you can do this. Another way of saying this, equivalent way of saying this, or if the integral is path independent. So, you have, even just in one dimension, you have some x initial, x final. If the particle moves this way, and then this way, and then this way, and then this way, and then eventually goes back to x final, if you can evaluate that integral and it equals just the value of some function evaluated at the final point minus the initial point, then that value should be exactly the same as if that particle went straight from the initial to the final point. So in 1D, this just means, back and forth is the same thing as just going straight there. In multiple dimensions, this is going to, visually, you can imagine a whole bunch of different paths from one point to another. So we'll have more to say about this mathematically with some fancier calculus things. Let's hold off on that for now. Okay, so now we want to connect this to the work energy theorem because I want to say something about kinetic energy as well. So now let's assume F. So there's only so F is the net force, so that this work is the net work. And I can do that, and if I can say that, then the work is equal to the change in kinetic energy from the work energy theorem. So to connect this to kinetic energy, I'm going to have to do that. So delta KE is equal to delta G, and we're going to define a new function. Define U of x is equal to minus G of x. So G of x was the antiderivative of F. And then U is going to be just minus that function. Now this, you can only do this, remember G only exists if this condition is true. If the integral is path independent, then G exists. Okay, so this function U only exists if these things are true, if F is conservative or if the integral is path independent. So this U of x is called the potential energy. So there are some forces that have a potential energy function, and there are some forces that don't have a potential energy function. That's what we're saying so far. Okay. So just playing around with this equation a tiny bit more. So if we add delta U to both sides, so we have delta KE is minus delta U. So if we add delta U to both sides, we have delta, and I'm going to switch colors because this part's pretty important. We have delta KE plus delta U is equal to 0. Or another way you could write this is, and by the way, your book is using K instead of KE, so maybe I'm going to switch from KE to just K now. So delta K is K final minus K initial. Delta U is U final minus U initial. So another way you could write this is K initial plus U initial is equal to K final plus U final. And we define, so this is kinetic energy and potential energy. We define the total amount of kinetic plus potential to be the mechanical energy. So the initial mechanical energy is equal to the final mechanical energy. So all of these statements are saying the same thing. And this is called conservation of mechanical energy. So this is true, this equation is true if there are no non-conservative forces. Okay, so what this is saying is that there's some total amount of energy. Remember, energy is just a number. It's some scalar quantity. It has units or dimensions, but it doesn't have a direction. And this energy can change forms from kinetic to potential. So maybe you reduce your potential energy and you increase your kinetic energy as a result. So gravity is a great example of this. You drop a rock. Maybe the rock is initially at rest. So if you drop a rock that's at rest here, it'll fall down. So what happens is the initial kinetic energy is 0, but the initial potential energy is some positive value. And then by the time it gets down to here, your final kinetic energy is equal to some positive value, and your final potential energy might be 0. Okay, so the addition of these two is the same though, 0 plus whatever positive amount of potential energy you have, and all that potential energy is converted to kinetic energy. And then there's no more potential energy left over. So really the potential energy could get negative. So maybe you dig a hole right here, then that U could become even negative, and then you get even more kinetic energy. So the rock could keep increasing its speed below, right? So the fact that it's 0, we're calling this U equals 0 is kind of arbitrary. Okay, so I'll say more about non-conservative forces when we get to friction. So let me give you a little table here. So conservative forces, some common ones that we'll look at are gravity, the gravitational force, and the spring force. Non-conservative forces, S-E or V, non-conservative forces. Friction is the best example of this, or maybe the drag force. Okay, dissipative forces. These forces get rid of energy out of the system, and there's no easy way to get it back. Okay, so this word conservative versus non-conservative, there's no political association with this. This is you should think of conservative in the sense as like conservation, so we can get that energy back again quickly. Maybe a mass is going quickly and it collides into a spring. That spring stores up the energy, and then you can use that energy to shoot the mass again. Okay, so you can get all that energy back, assuming none of it is dissipated due to like a drag force or a frictional force. Same with gravity. You throw a rock up, and that rock is going to come back down. So that energy is just being stored temporarily in the potential energy as the kinetic energy goes down, and then you get that energy back again. So the way to think about conservative versus non-conservative is that we can get this energy back again. And these over here, once the energy is dissipated, so the frictional force, you have some object moving along, it heats the surface up. You can't easily turn that heat energy back into energy of motion. So we can't easily. So energy is still conserved in this sense, but mechanical energy is not conserved if you have one of these forces. You can't easily get this energy back. So we'll explore this more when we talk about thermodynamics in the next course, about why it's difficult to get it back. But we need to study things like heat and all that. Okay, so conservative forces. So like we said before, conservative forces have a potential energy function. Okay, so it's a way of keeping track of how much energy is stored with these things. So we want to talk about there's a function U sub g, the potential energy stored in the gravitational field, and then the spring potential energy. So I'll use the subscripts G and S for gravitational and spring. UG is mgy. So the y direction is vertically upwards, meaning the higher and higher you get in this gravitational field, the more potential energy you have, the bigger U gets. And our equation for energy just deals with energy differences. So notice we're never talking about U by itself. It's always in an equation where it's U final minus U initial. So because of that, it's arbitrary where you set y equals 0. You can set y equals 0 wherever you'd like for a problem, because all that matters is the delta y. And delta y doesn't matter where you specify y equals 0. You do have to specify the plus y direction to be vertically upwards to use this equation with a plus sign right here. But you can set y equals 0 wherever you'd like. So normally the easiest thing to do is just wherever the smallest or the lowest thing in your problem is, I like to set that equal to y equals 0. So like in this problem right here with this picture, I'd probably set y equals 0 down here, and then up here would be y equals plus h, just to minimize the number of minus signs. And this will make everything easiest. All right, so just set the lowest wherever the problem is to y equals 0. So that's gravitational potential energy. Now for spring potential energy, and your book derives these too. So I'm skipping a little bit of what your book does. Your book is using the force. So the gravitational force is a constant mg, and when you integrate that, you get something proportional to y. Okay, so I'm sort of glossing over that. You can take a look at your textbook for more details. But that's exactly why, it's a force, and then integral of a constant is just a y included. So that's where that comes from. The spring force, remember, from Hooke's law is minus kx. So if you integrate minus kx with respect to x, you get a 1/2 x squared, 1/2 kx squared. So the spring potential energy is 1/2 kx squared. And keep in mind that x, so you might see this as delta x squared, or if you define x equals 0 to be when the spring is in equilibrium, you can just say 1/2 kx squared, and that's what your book does. Notice how they just write 1/2 kx squared. So physicists are lazy, we don't like to write the delta all the time. So we often set x equals 0 to be the relaxed location of the spring, to be where spring is in equilibrium, to be equilibrium spring. So x is just keeping track of how much the spring is either compressed or expanded. And notice because of the squared, it doesn't matter whether x is positive or negative. So if you take a spring and you stretch it by 1 centimeter, it's storing the same amount of energy as if you compress it by 1 centimeter. So it doesn't even, so x is just keeping track of how much the spring is either stretched or compressed relative to its relaxed length. And that's how much energy is stored in that spring. Okay, so overall, if there's no non-conservative forces, if we don't have to worry about friction or air resistance or losing energy, then we can set our mechanical energy initial. So if our mechanical energy is conserved, then we have our initial kinetic energy plus, and then if you have more than one kind of potential energy, you just add all of them. You add all the ways that energy could be stored up. So plus our gravitational potential energy initial plus our spring potential energy initial is equal to the final value of those quantities. So maybe the spring was initially compressed and then it shoots something off. And then, so in that case, the final potential energy of the spring would be 0 because it gave its energy to something else. So initially it was compressed, there was some positive potential energy. And then that goes to 0, and then one of these two would increase as a result. So if you fire something vertically upwards, maybe the gravitational potential energy is going to go up. Or maybe if you fire it horizontally, it's the kinetic energy that goes up, and it just remains in motion. So actually, if you fire something, the kinetic energy is definitely going to go up first, even if you fire it vertically, but then the kinetic energy goes down and gives its energy to you gravitational. So at any moment, you just pick any initial moment, any final moment, energy is conserved. And so as long as you're keeping track of all the energy, it's the same number on both sides of this equation. Okay. Now, unfortunately, we're still not in a position to do this problem because there's friction here. And friction's a non-conservative force. So if you have friction, and this is the point of this next section, friction and the work energy theorem. So if you have friction, or in general, any non-conservative force, then that force will do some work on the system, in general negative for the two we've thought about. So for friction or air resistance, it's going to take away energy from our system. Right? It does negative work on our system. Does an external work, does work that does not have an associated potential energy function. So therefore, we have to explicitly compute the work. And the equation that results from this, and this is very easy if you just think about where the energy is going. So you have some system with some initial kinetic energy, has some initial potential energy. So I'm going to use U to be the sum of gravitational and spring energies. So this is the total potential energy from conservative forces. So this is our initial energy, and then I'll put a blank there for now, is equal to our final kinetic energy plus our final potential energy. So this thing in here is going to be how much energy is transferred into our system. And most of the time this is negative. So this is going to be the work done by our external forces. This is the net work done by external forces. So you might say, well, what about the work energy theorem? I thought the work energy theorem deals with, so change in kinetic energy is work on the system. So what are these extra things, U? Well, maybe I should put, the best way to think about this is our system will include everything involved in the potential energies here. So let me give an example. If you have, so we already have an example set up in the problem statement, right? We have a hill. So our system is going to be the spring, or ball, or whatever we're shooting, and the earth. So the gravitational potential energy, so as this thing goes down in the gravitational field, this goes down, this goes up. There's no work external done on this system unless some energy is taken out of that. Ooh. Maybe this isn't making too much sense. I think this equation is best interpreted as you have some nice energy that you can get back again. You know, these energies can change forms back and forth into each other, but you can lose some of it due to some non-conservative forces. So that's a net work done on the system, which is negative for dissipative forces. So you might see the equation this way. You might see initial mechanical energy is equal to final mechanical energy plus whatever energy is lost due to friction. And so if it's written on this side of the equation, if it's written on the right-hand side, your final mechanical energy is less than your initial mechanical energy. So this would have to be the positive amount, plus energy lost, the absolute value of the energy lost to dissipative forces. Okay, the best illustration of this, I think, is to go over the example problem that we have. Okay, so we have a mass that's compressing a spring at distance d initially. Compressed to distance d. So there is some initial energy stored in the spring. And relative to our final position, we're starting off at with some gravitational potential energy. So I'm going to say that our y equals 0 is here. This is 0 gravitational potential energy is down at the bottom. So we have, so for our original problem, we're going to define our initial moment to be when the spring is compressed. And y equals h there. And then the final is after the thing comes to rest. After coming to rest. Okay, so our E mechanical initial plus the work done by our non-conservative forces is equal to our final mechanical energy. Our initial energy is our initial kinetic plus, and so you should start off every one of these problems the same way. Initial energy equals final energy, and then keep track of all the things that are contributing to the energy. So here our initial kinetic energy, initial gravitational potential energy, our initial spring potential energy, plus our work done by friction. Is equal to the final values of those things. So now all of these are actually 0. So the spring is no longer compressed after the thing shoots off. Our final potential energy is going to be 0 because we have, well, maybe this is clearer if I do one more step. So let me plug in what you would plug in for all of these. So mgy initial plus 1/2 kx initial squared. And then the work done by friction is always negative. So this is minus mu sub k mg. That's the magnitude of the frictional force, which is a constant magnitude times the length over which that thing slides. So remember, work is force times distance. If it's the integral of f dx, if f is constant, you could take it out of the integral sign. So f delta x is this. Is equal to the final values of the kinetic, the final value of potential energy, and the final value of the spring potential energy. The spring is not compressed or expanded finally. Our final y value is 0. We're going to set that equal to 0. And then the thing comes to rest finally. So our final mechanical energy is 0. Our thing wasn't moving initially, but it did have some non-zero gravitational potential energy. It was mg capital H. And we did have the spring compressed a distance d. Okay, so those two things were positive. Minus mu sub k mgl. And then we're asked to solve for the coefficient of friction mu sub k. So we have mu sub k. If we move this over to this side and divide by mgl, looks like we have h over l plus kd squared over 2 mgl. And that's it right here. Okay, we'll continue with non-conservative forces in multiple dimensions next chapter. But the point of this video is initial energy equals final energy. You just have to be a little bit careful if there's some non-conservative forces that can take your energy, your nice energy, your mechanical energy out of your system.